Good day, everyone. Nice seeing you again, or I should say, nice seeing you again. Welcome back to class, physics class. Today we are looking at deformation of solids. That's what we're looking at. And when you're talking about deformation of solids, you are talking about changing the shape of the solid by application of forces. Okay, we have two types actually. We have two types. We can have compressive force. We can have tensile force. When you talk about compressive, we are talking about the forces being applied, towards at both ends, but bringing the object together. For example, look at something like this. I have this object. If I apply force F1 and force F2, such that two of them, is towards the object, so this object will actually, compress, or you can say there's going to be decrease in size. Of course, is that okay? But if the object is elastic, which I will talk about very soon, if I remove the forces, it's going to come back with gain its shape. The second one is tensile. Tensile is when you apply the forces such that it tear the object apart. The same two forces, F1 and F2, that I applied earlier on, but now I'm bringing it outwardly, thereby tearing the object apart. So these are the basic two situations we have. Alright. Now, like I said earlier on, if this object is elastic, if it obeys Hooke's law, then when we remove the forces, it's going to regain its shape. Alright. Of course, I think we should talk about Hooke's law quickly. Hooke's law states that the extension produced by an elastic material is proportional to the force applied, provided elasticity is not exceeded. What are we saying? What we're saying is that if you have force applied to an object, the extension produced, force is proportional to extension, which means that we can say F equal to KE. Alright? Where F is the force applied, small letter E is the extension produced, and by the time you complete the expression forming an equation, you introduce a constant K. This constant is very important for us. In physics, this constant represents ratio of force against extension, and it's called the spring constant. Okay? Spring constant is a constant that determines the level of extension an object will experience before it's going to be deformed, and it has different values for different elastic materials. If the value of K is very small, it means the object will give way if you apply just minimal force. But if it's a large value, like 500, for example, then that means it has the ability to accommodate larger number of forces. Now, before we proceed, let's look at the unit. For this K is measured in Newton per centimeter. Okay? Of course, force is in Newton, extension, small extension in centimeters, so that's the unit of spring constant. Now, since we've discussed about Hooke's law, let's look at graph representing the relationship between force and extension for any material. Now, I have my graph force on the y-axis, extension on the x-axis, and when the force was applied to that object, we keep recording our values and the graph was plotted. Region where from the origin from O to A, that is region where Hooke's law is obeyed. Meaning that if we remove or take away our force up to this point, the material the extension will, its proportion is, it will regain its shape. Alright? Now, if you extend your force, if it goes beyond this value, the more force you apply, you're not going to have a proportional extension again. Therefore, the graph will not be a straight line. It will be a curve. Alright? So, and if that should continue up to region B, that's the limit to which the material can withstand. Anything beyond that is going to get properly, it's going to be permanently deformed. Are you following me? Now, if you get to that region, and if you now start removing your forces from it, gradually, this dotted line represents where, so it's not going to, so region OC is what's referred to as the region of permanent deformation, meaning that the object did not go back to its former shape or original shape. Alright, so this is a graph for such. Now the next thing we needed to look at is what is called stress and strain. For that system, you know, every object you can determine their area, surface area. If it's a cylindrical shape, you find the diameter or the radius, and you apply mathematics to get the area. So the ratio of force over area of on that object is what is called stress. Stress, rather, it's called stress, and is measured in Newton per meter square. The same unit that we have for pressure. Remember, pressure is force over area and is in Pascal. So stress and pressure, they have the same unit. Strain is the ratio of extension. Extension meaning that the increase in length divided by initial length. Strain has no unit because we have extension in centimeter or meters. You have length, initial length in centimeters. So strain is referred to as a dimensionless quantity in physics. Okay, it has no unit. All right. Now, if you now combine your stress and strain, you have what is called Young modulus. Young modulus is the ratio of stress divided by strain. Okay, stress over strain, and you know that stress is force over area multiplied by strain, which is length over extension. Extension over length, like we said earlier on. So when you combine two of them, you're going to have FL over volume. Of course, the volume was obtained because area times length is volume. So we can as well get it. So we can come across a calculation where they give you volume of the material. You have to find your modulus. Just multiply the force and length, and you get to where you are going. Now the last thing that we need to talk about is, when I apply force to any elastic material, when the material extends, don't forget, if I remove one of the forces on that object, if the object is still elastic, if it obey Hooke's law, if the elastic law is not exceeded, it's going to go back. It's going to move back to its initial shape, get the initial shape of initial length. Now, in doing that, the object must have worked. For it to work, it must have energy. Now, the point is this: where is the energy coming from? The energy must be coming from me. So, what I'm trying to say is, once you extend it, you transfer energy to that material. So the material will store the energy. Alright? That energy is what the material now uses to extend itself, to go back to its former position. Now, watch this. To determine the energy stored in elastic material graphically, what we do is, in our force against extension, you take note of the region, the straight line region of your graph, determine the area under that region. In this case, I have a triangle. Area of a triangle is simply half base and height. This is something you know in mathematics. Half base multiplied by height, which will then give me half force multiplied by the extension produced. Alright? Don't forget that from Hooke's law, F equals to KE from Hooke's law. You may as well proceed by saying energy stored is equal to F is KE multiplied by E, and that should give you KE squared. Alright? So you may use F equal to KE, F equal to FE, half FE, or we use half KE squared. So depending on the values that is available to you. Alright, so this is how far you go for this at this time. Ensure you cross check, make necessary clarification, and ask questions if you have any doubt. Thank you. See you some other time. Bye for now.